So we are having some technical problems. We are trying to figure them out as usual. It happens in place talks, so
yeah.
obviously.
Oh yeah, I have Wenzel Jakob now coming in, so I can admit him. Okay, I think he is. Hi, Wenzel. If you are talking, you're muted. Okay, sure. Thank you. Perfect.
Now.
I think we can hear you now.
Works, yes.
Yes, it does. So I'm gonna switch to the speakers. Okay. Awesome. For the people on YouTube, because I don't know if you're seeing the chat or not on the YouTube stream, we're having some problems, so just hold on for a few seconds or minutes.
Yeah.
We'll
Okay, so you are now sharing screen and it's working just fine.
yeah. No, I don't think so. Can you hear us? Okay. Now we can hear you. I think like. Oh, there you go.
What about now?
Oh, perfect.
Yeah.
Yeah,
Now it works.
that was fine. Yeah.
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 That was just the source of the.
Okay. But can you see my screen?
Yeah, we can.
Yes.
But which one do you see? Because
now we are seeing the mid one. The one with the
the what?
meat. The one with the
one with meat.
browser. Yes.
Okay. And so do you know if there's any way to switch that around? It never offered me the possibility to select which screen I want to share.
In theory, if you hit when you hit present your screen, it should be able to allow you to select what application you will be using. By the way, now the video works.
Yeah, okay. It only has one option, which is your entire screen, present your entire screen, and then it doesn't.
Yeah, Google Meet doesn't work very well with any other browser than Google Chrome.
Oh, okay.
Oh, well, okay, that's bad. So.
But can you move the? the slides here.
I can try and find a workaround, but okay, let's try the following.
Okay.
Oh,
yeah. Now it's perfect.
Okay, you see the slides only?
Yes.
Okay, all right.
Yeah.
Then let's try and get started with that, and then I hope all works.
Okay, so I will introduce our speaker. Today's speaker is Professor Wenzel Jakob from EPFL at Lausanne. He's the leader of the realistic graphics labs in that university. And well, his research spans around inverse rendering, material appearance modeling, and physically based rendering. He has done numerous contributions in the field, not only in just academic work, but also in the form of widely used code that has been used for almost 10 years in rendering quite extensively, including the Mitsuba renderer that some of you are already aware, the Nori renderer that we are using for the realistic graphics course. Plus, he's the author of the third edition of physically based rendering, together with Matt Farr and Greg Humphries. He has received several awards, including the ACM SIGGRAPH Significant Researcher Award and the Eurographics Young Researcher Award. And very recently, he got an ERC starting grant. So yeah, in topics related with what he will be talking about. So we are very lucky to have him here today. Thank you, Wenzel, for being here. And yeah, it's all yours.
Thank you, Adrian. So sorry about these technical issues again. I guess as part of this lockdown, I have pretty much all of the applications installed on my computer, Skype, Zoom, WebEx, what you can name, but this is the one I hadn't yet used. So invariably, it seems like it ran to every technical issue you could possibly have with it. Anyway, today I'm going to talk about differentiable rendering. If you have any questions, just interrupt me, or we can also do some Q&A at the end as you prefer. And so this title says it's going to be an introduction to differentiable rendering, but here it's a little bit unusual in that differentiable rendering is really something new. So we're not going to talk about a well-understood topic, but things where still are, things are maybe still a little bit broken, and I'll try and explain to you where we are now and where things are going to be going. So let's talk about rendering first, because differentiable rendering is a kind of rendering. And so when you work with a renderer, you normally start with some kind of a scene description. So we have the shapes, materials, positions of a variety of objects. And then we can run the renderer, and that's going to produce an output image. And what we'll do now, and in the rest of the talk, is that we will think of these inputs kind of like as a vector of numbers. So that includes all the texture parameters, vertices, and so on. So it's just one big vector that we put into a function f that's going to represent the rendering algorithm. And then after that's done crunching the numbers, it produces an output vector y that contains all of the pixels of the output rendering stacked on top of each other. So this step of converting the scene description into the realistic image, that's called rendering, and it's something that we understand pretty well at this point. And so in this talk today, I'm going to be focusing mainly on the other direction. That's called inverse rendering. And so the idea is, if we have an image of something, can we figure out what is actually visible in that image and then turn it back into the original scene description? And so this turns out to be a much harder problem. And it's particularly difficult when you're looking at realistic simulations. And so you may have noticed that there was this word physically based in the title of the talk. And so let me just explain what that means first in the context of ordinary rendering. So this is actually a photograph. It's a picture I took on my balcony to motivate some of the challenges that appear when you want to simulate light correctly. And so here we have sunlight that's coming from the left side. It's bouncing off this book, which is red, and you can see how some of that red color is transferred to the other objects. There are reflections, shadows. This glass pitcher of milk is refocusing some of the light into these interesting patterns that are called caustic. Some of the other light that gets into the milk kind of bounces around inside the milk. It enters all of these little fat bubbles that make up the milk and then bounces around. And that's actually what makes milk have this kind of glow that we consider that realistic. If it didn't have that, it wouldn't look like delicious milk. And then there are scratches, all sorts of imperfections. And all of these things are happening always, all the time. And so normally when we work on rendering, we work very hard to recreate all of these effects because they are what will ultimately make that image realistic to somebody who is looking at it. But remember that I mentioned we're not interested in rendering today in this talk. We're interested in going the other way. So we want to actually start with an image like that and then figure out everything that's inside this image. And that's much more complicated now because you have to understand that all of these objects are interacting with each other using light and then correct for that. So imagine this laptop, for instance, that you can see in the background. It's kind of reddish on some parts of it, but it's not actually red, right? It's only red because there's a reflection of another object that was red. And so when you try to understand what that laptop is made of, you have to understand those kinds of things so that you can really infer that actually it's just gray metal. The object is not really red on its own. So suppose that we have an algorithm that allows us to do this, basically, to go from a picture of a virtual world to the virtual world itself, or a picture of the real world. Then what can you actually do with that? So let's actually look at a few examples where this inverse and differentiable rendering that I'll talk about later are going to be useful. So the first one is kind of as a way of saving time when modeling things. Imagine that somebody gives you these 4 pictures of a 3-dimensional object, but you don't actually have the 3-dimensional object itself, but just these pictures. And now you want to recreate the associated object. Then the idea with this inverse rendering is that you can start with a very poor approximation. So here it's just a sort of a template shape that has the right topology. And then we optimize the difference between those two. This is what you can see in the middle. And you can see how the shape is evolving. It's becoming closer and closer to the output images that you can see on the right. The color is changing. You can see how the algorithm is pushing out all of those little bumps. And then over time, we have a pretty good approximation. Now here that was done actually to recreate a rendered image. So it's not too surprising that that works. But we can also do it with a real world object, like the pear that you can see here. That was a photograph. And so we start with this green blob on the left side, and then we try to minimize the difference to the actual reference photographs, and then progressively we can reconstruct the material, the shape, and really take also into account all of the cues that are in this image. So for instance, this pear casts some shadows, and these shadows actually provide clues about the height of the surface in different parts. So I had mentioned how rendering is this very global effect, right? We have light that is scattered off an object, and then it interacts with other objects as well. And when you have a renderer that you can run in the opposite direction, then it allows you to do interesting things with these indirect effects. So imagine that you have a glass with some liquid and sunlight shines on it, then it creates these interesting patterns that we saw before, which are called caustics. And an interesting question that you can ask is, can I design a particular piece of glass that will produce a certain caustic? And this is something that you can actually do if you have access to this kind of an inverse simulation. And here's what that looks like. So we're in a museum. There is a glass slab. Light is being focused on that glass slab. And now we're optimizing that so that over time, it becomes a rendition of the Great Wave by Hokusai. And so what we have now in the end is no longer a flat glass panel. It actually has some height variations. So it's a height field. And those height field values are very carefully computed so that when you shine light at it from the right direction, then it recreates that image. So here we're kind of stretching light and we're compressing it so that we get the right grayscale values. And that's what these little height variations on the surface do. But using really the same algorithm with no changes, we can also solve another kind of problem where instead of just stretching and expanding light, we are really bending it around to mix it to create a color image. And so here we're starting just with these generic red, green, and blue colors, And we're using that now to try to reconstruct a painting. And you can see that over time, we get closer and closer to that. Now, there's a lot of garbage kind of around the image, and that's just because we're only optimizing the center part. So that's another example of something you can do with an inverse renderer. I'll give one more example, and that's 3D printing. So nowadays we have lots of fancy 3D printers, and some of the most advanced ones can actually put down little ink droplets while you're creating a three-dimensional object. And so that means you can really put any color pattern on this object, and people immediately started trying to play with that and found it a little bit disappointing, because the thing that comes out in the end of this print normally doesn't look like what you really wanted. And the reason for this are the physics of light. The materials that you print with are normally very translucent, and so light actually goes inside and it bounces around and then comes out somewhere else. And as a consequence, you lose a lot of the contrast of the original pattern that you wanted to print. This can also be formulated as an inverse problem. And so the idea is you say, what kind of ink droplets do I actually have to put so that taking all of this light scattering into account, I get the pattern out in the end that I wanted. And so here's an example of that. We can start with some kind of a reference. And then when we turn on subsurface scattering, it becomes translucent. We lose a lot of the contrast. Look at the clouds, for example. And now we can run a volume renderer that actually correctly simulates that and try to recover some of that contrast. And then we can improve it. It's not a magic bullet. We don't get all the way back, but we can definitely do better. What I really like about this idea of running rendering algorithms in the opposite direction is that it creates many connections to other fields. So think of architecture. That's just in one of many possible examples. Normally, when you're inside a building, it's really bright close to the windows, too bright almost. So you need something to avoid the glare. And then when you go further into the building, then it's too dark. And that means you have to add a lot of electric lighting. Now, a famous architect will think of this building really like a kind of an optical system and think of how to use as much natural light as possible, because this will, that's of course always preferable to adding a lot of electric lighting. But this is a very complicated optimization problem. And this is a kind of a situation where such an inverse renderer can help, because we can actually ask it, how should we change the building so that we can get closer to the kind of lighting goals that we're trying to achieve? So that's kind of the motivation of inverse and differentiable rendering. But I haven't really explained to you what exactly differentiable rendering is and how it works. And so I'll try to do that now while looking at a really simple toy problem. So this problem is maybe not yet quite realistic of some of the actual things that we want to solve with it, but it's really just a way to learn about some of the involved mathematics. So here in particular, let's say that we have this image of a virtual scene. This is a virtual scene containing this T set on a table. We have all the files that we need to render that, but we're not quite happy with that image. Instead, we would like it to look something like this. And so basically, we want to change the pattern on the teapot. But we don't have access to the texture that contains this swirly pattern. And so this is now something that we will try to reconstruct using an inverse renderer. We're not changing any shapes in this example. And so that's something I will actually get back towards the end of the talk. OK, so now we have to write down what is the problem that we want to optimize. And so for this, we need an objective function. The objective function quantifies how good the current scene is. So we can plug in the current scene, and then we can render it. And then we can take the difference to what we really want the rendering to look like. And here, it's just a simple L2 metric. But in principle, this could be any metric that's potentially much more complicated. All right, and then the inverse rendering problem is that we plug our rendering algorithm into this objective function. We have our scene parameters, and then we just want to minimize that. All right, so this is what it looks like in sort of a block diagram. The space X, again, that's the scene description, and it's very high dimensional. This could have 10 or 100 million different parameters. And the scene, it consists also of many different things. It's first of all the meshes, so the three-dimensional shape of the various objects. The material parameters is something, a piece of metal or a piece of glass. There might be three-dimensional textures applied on top of things. There might be more complicated algorithmic definitions of models. Those are called procedural. We can have light sources, volumes, and so on. And all of these things are something that we want to optimize it. Now this gets plugged into an objective function, and this objective function provides just one number at the end. That's called z. So this is one number that quantifies the quality of the current solution. This objective function maybe also makes use of some reference, and then we can run gradient descent to optimize this minimization problem. And that's basically one of the key things that makes this possible. The original optimization problem is maybe very complex and we probably cannot directly write down an analytic solution unless it's greatly simplified, but gradient descent provides us a way of walking in the right direction in this high-dimensional parameter space to try and get closer and closer to a good solution. Now, there are some things that we can do to simplify this problem a little bit further. And so the first one is to realize that here, what we want to do now is to differentiate two functions that are nested inside each other. And in that case, we can make use of something that's called the chain rule. So the chain rule allows us to partition this differentiation process into differentiation of two separate functions. So first, we divide the outer function, we differentiate the outer function and then the inner function. And so what that means here is that, first of all, we differentiate the objective function, and that gives us an image that looks kind of like this. And that image basically tells us how we want the rendering to change. If a pixel in this image is positive, then we want that pixel to become brighter. And if it's negative, then we want it to become darker. And this picture, we will think of it as a kind of a vector. And then this vector has to be multiplied with a matrix, and the matrix describes the rendering algorithm here. So we have to basically convert now these desired changes in the image into desired changes of the scene parameters that define this three-dimensional model of the world. And so this is really the main complicated part. So let's forget about everything else and just focus on how we can take these derivatives that we have in image space and convert them into something that can be applied to the scene parameters. And this, by the way, is what the image looks like. So you can see we want to change the pattern on the teapot into this swirly pattern, and that also shows up in this difference image. But because rendering is a very global process that also has an indirect effects on other parts of the scene. And so here we also want to optimize the reflection of the teapot in the shiny table that it's sitting on. All right, so we want to understand basically this matrix multiplication that involves derivatives. And I'll talk about three things. So first of all, how to do it in general. That's going to lead us to an algorithm which works, but it's not very efficient. Then we'll talk about efficiency. And then finally, I'll explain how to optimize also shapes. And optimizing three-dimensional shapes is a little bit more complicated because that involves visibility changes, which are discontinuities. And discontinuities, as you know, are something that's not differentiable. And so that requires some special tricks so that it makes sense in this whole framework of differentiating algorithms. Okay, so let's start with some basics about rendering first. A rendering algorithm solves a very famous equation that's known as the rendering equation. And the rendering equation basically tells us how much light goes into a particular point and relates that to how much light comes out somewhere else. And I can try and explain it visually in this example of the Cornell box, which is a very famous scene that people often look at to understand light transport problems. And so what you can see in the scene on the left is that there is a black dot that's moving around on the ceiling. And now suppose that we wanted to compute the color of this moving black dot. Well, to do that, you can take a look on the right side of the slide. There is an integral that's being computed there. And this is actually the computation that we have to solve to determine this color. Now, in this integral, which, by the way, is an integral over the sphere, there are two functions that are showing up and they're being multiplied with each other. The first one is the incident illumination. So that's all of the light which is arriving at this point. And so you can think of this point as sort of like an ant that's looking out into the hemisphere below it. And this is what it's seeing. And then this gets multiplied by something which describes the material. Now, in this case, the ceiling of this box is made of metal. So it's a sort of a shiny material. And what you can see is actually happening here is that the product of these two different spherical functions now kind of selects out a small portion of the function. And that's actually what's causing it to be such a shiny material that reflects light in a very specific way. Okay, so this is normally the equation that we solve in a rendering algorithm. And this is what it looks like when it's written out in a more formal way. And so in particular, we have the outgoing radiance at some point x in a direction omega. And this is equal to the emitted light, that's the LE function here, and an integral. So let's look at both of these separately. LE is basically non-zero when the object is emitting light itself. So for instance, this table here might actually be on fire, and then it would be an emitter, or it could be another kind of light source as well. So that's what the first part describes. The second part is an integral over the sphere. And so this looks at all possible directions from which light might be arriving. And then that gets multiplied by a function called the BRDF, that's this FS function. So this now characterizes the material. It's this thing from the previous slide that was almost black and then became non-zero in a small region. And so this will now influence what the material behaves like, depending on whether it's a piece of glass, a piece of metal, or just something diffuse like a wall or a piece of paper. And then all of this also gets weighted by a cosine factor, which I won't get into. So that's the rendering equation, but we're not interested in computing this equation. We are interested in the derivative of it. And so we have to differentiate everything that we can see here now. And I'll symbolize that using this green rectangle. So this is now going to be a derivative with respect to the parameters that define the scene. So I will differentiate the left side of the equation, but then I have to differentiate the right one as well. And now the first term that is affected by this is this emission term. And so what you can think of here physically is a kind of an analogy now. We're taking our original light simulation problem and we're turning it into a kind of derivative light simulation problem. So that's kind of as if we are looking at the scene, but using goggles that allow us to visualize a different kind of radiation. That's basically derivative radiation. So this is not quite like ordinary light, but let's just think of it that way for now. Okay, so what this equation is now saying is that the table will actually emit this derivative radiation if it's burning in a differentiable way. That sounds kind of strange. So what does that mean? It's basically saying that when there is a scene parameter that affects the quality of that fire, for instance, the color or how bright it is, then this object will actually emit this strange kind of derivative radiation, and it's going to be seen by the camera. Okay, so that's what the first part does. Let's look at the second part. This is an integral with a product, and so when we differentiate it, it actually expands into two things based on the product rule. Now, the first expression that shows up is an integral over the incident illumination multiplied by the derivative of the function that describes the material. And so what this is saying is that when you have a table and its appearance is affected by scene parameters, then this table converts ordinary illumination into this new kind of derivative radiation. And then the last part is the derivative of incident illumination multiplied by the material. And what this is saying is that when this derivative light arrives from somewhere else, then it bounces off the table and it follows all of the same laws of physical light transport. So it behaves just like normal light. Okay, so now we can summarize this a little bit. This differential radiance is actually emitted by different parts of the scene, and it's precisely those which have differentiable scene parameters. And then once it's created, this differentiable radiance bounces around through the scene as if it was normal light. And this is the key insight that will now enable us to simulate this derivative radiance. So for instance, let's say we go back to our teapot scene. This teapot has some kind of a texture on it. And here in red, you can see now one pixel of this, or one texel, I should say, of this texture being highlighted. What we can do now is to simulate the way that derivative radiation from this pixel propagates through the scene. And then we can see that when we change the value of this texel a little bit, then that's also going to have a larger influence on the scene, and that's now highlighted in red. And so this is what our differentiable renderer will try to estimate now. But remember that we weren't just looking at the effect of individual texels, but we wanted to solve a larger problem. And this problem was that we actually wanted to change the image in a particular way. So we were given this derivative image, and now we want to propagate that derivative image through the underlying computation, through the rendering algorithm, so that we can figure out how to update the scene parameters. And this is an operation that really happens in image space. And so we can go back to image space and then try and understand what's happening here. And now we have different kinds of gradients. So we have gradients with respect to scene parameters. Those are shown in red. That's what we had just a moment ago. There's a derivative with respect to the objective function. That's how we would like the image to change. That was this mainly black image that you saw before. And what we want to compute now is the dot product of both of these different signals. Each such dot product will give us will tell us how to change one texel of the texture that defines this teapot. And so we can fill that in the top left. That's going to be the gradient, the texture space gradient of this teapot. And so now we can just walk through all of the possibilities. So we can run such a differentiable simulation for each texel in this three-dimensional object. And then you can see how the thing on the top left is being filled in. This is now the information that we need to do one gradient step to basically get closer to where we want to be. Now, there are some unfortunate problems with this approach. And this is that when you have a 1 megapixel rendering and 1 million parameters, then this matrix that we need to multiply by is actually huge. It's going to be a 1 million by 1 million matrix. This would take 3.6 terabytes to store. And also, it would take forever to compute. It's not just storage that is the problem. And so this really doesn't work. And we need a more efficient way to compute these kinds of derivatives. So let's talk about that. Now, the problem that we just encountered, it's really representative of a particular way of differentiating calculations. And just to understand that problem, I'm going to look at a very simple calculation. So imagine that we have two numbers that we multiply with each other, and then we add another number to that. Then you can draw the computation graph of this calculation below. So we have the multiplication, the sum, and then the end result. And now let's say that we want to differentiate it. So we want to understand how y changes when we wiggle around one of the inputs, x0, x1, or x2. Then we can do that by basically looking at the influence of each separate parameter. We have to propagate those derivatives through the entire calculation. And then at the end, we get the gradient vector. And this is pretty much what we did just now, but for the rendering algorithm. And this is called forward mode differentiation. And when there is a forward mode, then probably, as the name kind of implies, there's also a reverse mode. So let's look at what reverse mode differentiation would do here. In reverse mode, you do basically the same kind of analysis, but instead of wiggling around the inputs to see how the outputs change, we wiggle around the output to see how the input changes. And this is vastly more efficient when you're working with a function that has many outputs, many inputs and only an output. So in particular here, we would then propagate the derivatives from y, and you can already see, even for this simple function, that we're just done much, much more quickly. So it seems that we are just using the wrong mode of differentiation. We should have used reverse mode differentiation for our differentiable renderer, and then everything would have just been fine. Unfortunately, there is a big problem with this, and this is that when we originally run this program, it goes from left to right. We are starting with the inputs, then we do all of the intermediate calculation, and then eventually we get some output. But this process of differentiating the thing, now this goes in the opposite direction, because we have to start at the output and then work our way to the input. And this is problematic because to be able to do the differentiation later on, we have to remember all of the steps that we ran in between. And so that leads to inefficiencies. We have to record a computation graph. If you've worked with TensorFlow or PyTorch and these kinds of frameworks, this is basically what these allow you to do. And so what invariably happens, unfortunately, when you try this with a rendering algorithm is that you wrap it into this differentiation tool, which it's called automatic differentiation. It's going to record the computation graph, and then after a short amount of time, it just explodes. There's no more memory. And the reason for this is that the computation graph became very large. In rendering algorithms, the computation graphs are really crazy. They become insanely huge. And the reason for this is the behavior of light. Light enters an object, it scatters, it reflects and bounces around, and it's not very structured. And so as a consequence, that's something that really makes the resulting graph of the computations very messy and difficult to keep track of. So this was the state about a year ago, which was a little bit depressing. So everybody was interested in differentiating rendering algorithms, and there were these two ways to do it. The first one is forward mode, which that works, but it's really painful to do it when you have a scene with many parameters, because you have to run a separate differentiation pass for each input parameter. And when you have millions of parameters or hundreds of millions, that's just not really possible. And then the other one was reverse mode, where the differentiation itself is much more efficient, but the problem is you run out of memory after a short time. And we tried all sorts of things to make it more efficient. We in our own research, we added a just-in-time compiler, ways of simplifying this graph, and it helped a little bit, but this didn't really solve the fundamental problem. And so what I'll show to you now is some recent work that we've been pursuing that really solves this memory problem. So you can now do differentiable rendering without running out of memory. And it's based on a really neat idea that's not from rendering at all. This actually goes back a long time. It's from 1962 to a method that's called the adjoint sensitivity method. And this is an algorithm that is traditionally used for ordinary differential equations. Now, if you remember ordinary differential equations, one setting in which they often come up is that you have a kind of a vector field and you have a particle. You start this particle at some point in time, and then you look at how it evolves as it moves through this particle field. So at some finishing time, you're now at a new position. But now suppose that you want to differentiate this program, just like we are interested in differentiating the rendering algorithm, and we're interested in differentiating it in reverse mode. Then that means that we have to be able to run the whole simulation once more, but we have to run it in the opposite direction, from the end to the start, because that is always what you have to do for reverse mode differentiation. You have to flip around the original execution. So this is what we want to do now. Well, it turns out that for ordinary differential equations, doing this reversal is actually kind of trivial, because all that you need to do is just to flip the direction of the time dimension. Instead of integrating forward in time, you can just integrate backward in time, and then you'll return to the position that you started from. And this generally works. And so that's kind of interesting, that when problems have this natural ability to be inverted or reversed in time, then differentiating them becomes very easy. And that's the idea of this adjoint sensitivity method. So the interesting question is whether it's maybe possible to do something similar also for rendering algorithms. And so the unfortunate thing is that normally we don't really care about time in rendering algorithms because light is moving so quickly. And even if we added a time dimension, then that wouldn't be helpful, because as light interacts with objects, it kind of spreads out in a way that loses information. So it's difficult to go in reverse and sort of bring it back and reunite it. And so it doesn't really have this convenient reversibility property that we would expect for an ordinary differential equation. But the name adjoint that occurs in the title of this method is a good hint, because there are actually also adjoint methods in the context of rendering, and it turns out that this provides the key idea to make all of this possible. So in the context of rendering, when people talk about adjoints, what they usually mean is this idea that the physical light transport laws are symmetric. And so that means you can send out light from a light source and then bounce it around and until it reaches the camera, and then that will give you a rendering. But you can also start from the other way. You can start at the camera and try to find the light sources, and that involves all the same physical laws, and the image that you will get out is also the same one. Now, sometimes one strategy is much easier than the other, so you get a rendering in a shorter amount of time. And so there are algorithms like bidirectional path tracing that exploit this by actually searching for connections from both sides and then trying to meet up in the middle. And all of this under the hood is based on this idea of self-adjoint operators. I won't have a lot of time to go into that, but it's really a beautiful part of computer graphics. And so this is what we will actually use now to enable doing differentiable rendering much more efficiently. Instead of sending out this derivative light from the objects themselves, we will actually send it out from the camera. You remember that we had this image on the camera that were the per pixel derivatives that told us how the output image should actually be changed. And so we will send this image out from the camera now. It's going to bounce around in the scene. If we were just doing a normal rendering of that, it would look something like this. So we're kind of projecting this pattern that we want in the scene onto the actual scene objects. Now, in general, we won't be able to really visualize this picture because parts of it will be positive and other parts of it will be negative. And so now we're doing basically the same kind of computation where we're sending out this radiation on the objects. That's the blue part. And then we want to compute also the derivative with respect to scene parameters. That's the red part. We want the dot product or the product integral of those. And then that gives us the gradients, which are shown in the top left. Now, it turns out that this way of doing it actually makes things much easier. So let me explain to you why. In a normal rendering algorithm, we have basically these two ways of propagating energy. We can start at the light source and then send out light or radiance and then bounce that around until it arrives on the sensors. But we can equivalently also start at the sensors and push out a different kind of energy that's really, it's not a physical quantity. Think of it as a sort of a hypothetical energy. And this is called importance. And that also bounces around and it follows the same physical laws. And that can sometimes enable building more efficient algorithms. And all of these quantities are spectrally varying. In a renderer, that typically means we have a red, green, and blue channel. Now, in a differentiable renderer, we're not propagating light, but we're propagating derivatives. So we're sending out derivatives from the objects and we're sending out derivatives from the sensor. Again, these are colored pieces of information, but they are now positive and potentially negative, which we want to decrease the amount of energy in some part of the scene. Now, the interesting thing, and that's really the key observation, is the dimensionality of this. There are millions and millions of scene parameters in practice. And so now sending out this energy from the objects and propagating it to the sensor is completely infeasible. Instead, it's much easier to start from the other side, from the sensor, send this derivative energy onto the objects, and at that point, will we only figure out what the gradients are. And so what that means in practice is that we're sending out this derivative radiation from the camera. At some point, that's going to reach a position on the object. And then we just have to understand, what is it that makes the object look the way that it does at that particular point. You'll remember from earlier, there was this function fs. That was the function that characterized the material. It depends on the incident direction of light and the outgoing direction of light. But then it also really depends on a few scene parameters. For instance, a scene parameter here might say whether that object is gray or whether it's white, whether it's made of metal or whether it's a glass surface. And so what we can do now is to further propagate those gradients into this function, and they will now change the properties of the surface at that location. And that leads to a really simple algorithm that's much more efficient. So let me show you a few examples of what you can do with that. I'll say ahead of time that teleconferencing software has issues with these videos because they're a little bit noisy. So I hope that you will actually be able to see anything. But let me just explain to you what you should see. So there is a a sphere that's under a glass bulb. The glass bulb is complicated and curved, and there are all kinds of reflections being shown here. And all of this is in a room, and the room only gets illuminated from the outside. Now, we're starting with the configuration on the left, and so that means this glass globe in the middle has the texture of the planet Mars, and we want to convert it into the planet Earth. But we don't have the texture of the Earth. We only have a reference image of what that should look like. And that's shown on the right. And the question is whether we can figure out what really the precise texture is on this globe so that it looks like the right image. And so here you can now see that optimization running over time. And watch how the optimized texture changes. That's the upper texture on the left side. You can see how it progressively gets closer and closer to this Earth texture. But there are some parts of it which still stay brown, and those are parts of the Earth that we just weren't able to see anywhere. And so you can see we're looking at the Earth from the front, and then there's a reflection in the mirror. But there are some other parts in the globe, like below the holder, that we just didn't see. And those, of course, stay the same during this optimization problem because they don't have an influence on the scene. And again, this is what it looks like when we just really magnify the globe itself. We start with Mars, and then it converts over time into this Earth texture. So this is a little bit of a contrived optimization problem. Let's look at something a bit more interesting. And so here we have a 3D volume. We're starting the rendering algorithm with a situation where the volume is completely uniform, and we want to recover the target volume, which is shown on the right side. Now, in the middle, you have this new algorithm that's based on directly propagating derivative energy through the scene. And on the left, you have a more traditional algorithm that's based on doing a simulation, recording everything, and then just running automatic differentiation on top of that. And so the middle algorithm converges very quickly. The left one is extremely slow, basically in the whole time where the middle algorithm converged, the one on the left didn't even do a single step. And we can look also at some performance numbers. And in particular for this volume density optimization, it's up to about a factor of 1,000 faster. So it makes a big difference to switch to this different approach to propagating derivatives. Okay, and so here's a summary of the main ideas. This concept of propagating derivatives through a rendering algorithm turns out much easier than many of us thought initially. It's just like another kind of light transport simulation, except that the sensors and the emitters are weird. So they are not the original sensors and emitters that you started with. And that allows you to convert everything into a normal rendering process. We can build on really decades of research that allow us to solve these kinds of problems. Now, in the remainder of the time, let me just very quickly mention one other problem that we often have to solve in practice in this differentiable rendering, and that's discontinuities. When you look at pixels in an image like that, or shadows, reflections in surfaces, very often we're computing integrals of things that contain discontinuities, and discontinuities are not differentiable. Now, the problem is not really that there are discontinuities, because we can perfectly well compute integrals of functions containing discontinuities, but the problem is that depending on the scene parameters, these discontinuities potentially move around. And this now is actually what's going to be the problem, because when we differentiate a rendering algorithm, this function f, with respect to some value x, what we really rely on this ability is that we can move the derivative inside the integral, and that normally works perfectly fine. But unfortunately, when you have these moving discontinuities, then that really just doesn't work anymore. So you actually get the wrong result. And in particular, we want to compute the thing on the right, on the left. The thing on the right is what we get when we differentiate our algorithm, and then those two are no longer the same, and that's really a problem. And so there was a wonderful paper in SIGGRAPH Asia 2018 that provided really the first way of solving that problem. And their idea was to look at to really search all of those discontinuities and place additional samples there to correct the error that's introduced by having these moving discontinuities. Now, the problem with that is just that finding silhouette edges or these discontinuities, that can be very difficult because you need a data structure to do that efficiently. And we haven't really found a very good data structure for doing that. And so that leads to issues with this kind of algorithm. And let me show to you another way of solving that problem. And this is what we're usually doing nowadays. Basically, all of these algorithms, they place random samples to compute these integrals. And those are these dots that you see in gray. And then there is a discontinuity, and this discontinuity is moving around when we change one of the scene parameters. And that's what's causing things to be wrong. But the problem is just that the discontinuity moves relative to the samples. If there was something that we could do to kind of keep the samples attached to the discontinuity, like what you see on the right, then there wouldn't be a problem. The derivative of this integral would give the perfect answer. And it turns out that we can actually convert the problem on the left into the problem on the right using a change of variables. We have to reparameterize all of the samples so that they move along with this discontinuity. And we can do that in a way that doesn't change the actual value of the integral. This is all described in a paper at SIGGRAPH Asia 2009. There are lots of little details that I won't bother you with, but here's just the key takeaway. So we can now differentiate shapes with respect to all kinds of changes, translations, rotations, shifts, of course, not just changes of the object itself, but also changes of individual parts of the object. If you don't do this change of variables, the gradients that you get are just wrong. They're almost zero. And then with these changes of variables, you can reconstruct the right value. And it also works for indirectly seen things. Here are examples of objects seen in reflections or shadows of objects, or objects seen through refractive surfaces. And it's more efficient than this edge sampling operation, especially as you work with objects that are finely subdivided. When you have more and more triangles, it gets increasingly complicated to find all of the edges. Okay, so let me just wrap up by saying that we're far from done with all of these issues that I mentioned today. In particular, one problem that we're still struggling with is that when you run differentiable rendering, very often the simulation doesn't converge to the right answer. And this is a major difference to neural networks that you can just kind of initialize randomly and then run stochastic gradient descent, and it will automatically find a reasonable solution. So for differentiable rendering, you often tend to get stuck in local minima that are really low quality. And so figuring out ways to avoid that is going to be an interesting challenge. And then for the optimization objective, currently we're mainly just taking differences between images, but this is probably not a very good choice. How to parameterize the scene in such a way that the simulation and the optimization gets easier is also something that will still need a lot of work. And so we're far from done, and it's going to be interesting to see how this will all look in a few years. So I'd like to acknowledge my students and postdocs who really did all of the work that I showed to you today. And one thing I just want to mention is that we're also looking for talented PhD students and postdocs. So if those kinds of topics are interesting to you, or you know somebody who might be interested, then please forward them this information. And that's all. Thank you.
This will be a bunch of claps. That's the issue with Telecom. Thank you very much for the talk. It was super great. So we have time for a few questions. So yeah, don't be shy and just ask. So yeah, go ahead, Jorge. So the first question is related with the gradient-based inverse rendering you mentioned. How does this differ from GAN-style networks? Mm-hmm. And how does differentiable rendering, the example you used for texture replacement, compare with cycle GAN-based solutions?
Okay. Yeah. So I guess rendering tends to be kind of slow, right? It can take can easily take a few minutes to produce one image, and so actually quite early on, people have looked into replacing the rendering algorithm just with a neural network that you can kind of train to reproduce the effects of rendering. And that's, of course, something you can do. And this is really a parallel line of development. So it's a different group of people who are working on those kinds of algorithms. As for myself, I'm more interested in really doing the simulation correctly instead of offloading it to a neural network. Part of the reason is that a renderer, it solves some physical equations, and we actually understand these equations really well. And so yes, you can train a neural network to kind of learn those same equations, but why go through all of those difficulties when you already know what the right answer is? So I'm thinking of that as just a kind of a heavy regularization strategy. And I think it's going to be interesting to look at combinations of rendering algorithms and things like GANs, where you can maybe produce scene contents using a GAN, but then they're simulated using a correct rendering process that accounts for all of the physical laws.
Thanks. Is there more questions? Come on, just ask. Well, in the meantime, let me ask you someone. Something that it's to me interesting about this differentiable rendering is how you can. Is there any way that you can use it not for just you can inverse rendering, but is there any way of using that also for improving forward rendering? We have been using derivatives for photo mapping or for radiance catching, etc.
Yeah.
Is this some approach that could make sense?
Yeah, I think that's something that people had already looked at before. If you think about the work of Ravi Ramamurthy, he has a number of papers that look at derivatives of forward rendering. Relighting is actually a context where people were interested in this at some point, that you can, or not just relighting, but in production, that kind of this idea that you render a shot, which is going to involve a lot of computation, but then you want to be able to tweak things later on without having to do another whole expensive rendering. If you can change the light sources, maybe even affect the material parameters, and then have a very high quality preview, and then only then, when you've kind of converged with all your changes, do you launch another rendering. That's another interesting idea where derivatives can be quite useful, because they provide a local model of what the whole simulation behaves like around the current parameters. I think in terms of the tools that are involved, it's very different, because right now we are most interested in really this reverse mode differentiation, where we want to propagate derivatives from the output to the input of the rendering algorithm. And really the main challenge here is this different flow of execution that you have during reverse mode differentiation. And so in terms of the algorithms, it behaves really fundamentally different than this forward mode differentiation, which you would use in such an application like relighting.
Okay, thanks. Is there more question? So Miguel is asking a question here. I'm reading. I would like to ask, since the adjoint method is equivalent to the typical rendering scenario, I imagine that the gradients will have a certain amount of noise. Given the impressive results you present, it should not be a big problem, but I wonder if variance reduction techniques could be applied to reduce the error in your computations.
Yeah. Mm-hmm. Yeah, that's an excellent point. Yeah, so this adjoint variant of the rendering algorithm is really just like a normal rendering algorithm. So you get all of the typical undesired effects. You can have, fireflies and regions in the output that are contaminated really by excessive variance, except that the output of such an adjoint rendering algorithm is a little bit strange, because it doesn't really render an image. It renders to all of the scene parameters, and the scene parameters might be spread out between objects. A few of them could be textures, you could have some volumes, you could have individual scene parameters like the roughness of an entire object or so. And so all of these will be affected by a certain amount of noise. And so the nice thing is that typically this variance is really just variance. There's no bias. And so and we have algorithms like stochastic gradient descent, where we can, there's been a lot of analysis on the behavior of these methods with unbiased gradients. And so what you can always do is you can use more samples, right? That will reduce the amount of variance. You can use a smaller step size in stochastic gradient descent, which is really boiled down to the same thing. But then ultimately, yeah, what's going to happen is if your gradients are very noisy, then it's just going to require more computation to converge to a good answer. And so just like we have denoising techniques for rendering algorithms, I think this is actually a very interesting point. Is there something that we can use to denoise gradients, and that's going to provide us a way of doing larger steps in the stochastic gradient descent? Of course, then in that case, probably there's also some bias, and then would be interesting to understand how that bias affects the reliability of a gradient descent-like method that normally expects unbiased gradients. I think this is something we don't really understand very well at the moment.
So keeping on with that question, then I guess you also need to develop new important sampling strategies.
Yes, yeah, new important sampling strategies. That's something that we're already working on. Because now we understand the whole thing just like a normal rendering algorithm. That means, of course, you can plug in sampling strategies that are specifically designed to improve the rendering of gradients. That is something you can do. Yeah, and then for denoising also, I think the interesting aspect is all of the current denoising techniques, they're really based on the idea that you apply it to an image. We have machine learning-based denoisers that use convolutions, but what does it mean to denoise output parameters that aren't necessarily an image? We have all sorts of other parameters in a rendering algorithm that do not take that form.
So yeah, another question from Diego, not looking ahead. Is that could you combine forward rendering with inverse rendering to get faster results when computation gets too hard?
Okay. Trying to form a mental model of what that would look like. I would say that if your goal is only forward rendering, then inverse rendering is maybe not the thing that you want to throw at it, because inverse rendering is more complicated. It tends to run quite a bit slower at the moment. Actually, one interesting reason is that forward rendering, it's this kind of nice read-only operation. We send out rays, the rays encounter scene objects, and then we query their properties. And so everything, you have only read access to the scene. When you do differentiable rendering, you want to modify the scene. So all of the rays that you send out with the camera, they actually write to the objects to update the gradients that are stored there. So that alone, kind of from a computer architectural point of view, is something that's going to make things run slower, because it's more complex to track millions of writes that to various scene objects. So because of that, it's not clear to me how it would accelerate forward rendering. On the other hand, if you have a way of doing forward rendering faster, then inverse rendering will probably benefit from this as well.
We have a few questions on YouTube as well, because there's some people watching the stream on YouTube. One of them says, which are your thoughts about new imaging modalities to address the ambiguities of the inverse rendering problem?
You're going to have to repeat that. So to address the ambiguities of the inverse rendering problem, what is the idea?
So it says, which are your thoughts about new imaging modalities to address...
New imaging modalities.
Yes, sorry.
Okay. Yeah, I mean, the more information you have about something, the less ambiguous the problem becomes. And so what people do nowadays is that instead of running the inversion just on a single picture, you use a few different viewpoints. I mean, that is something that is definitely a problem. Imagine this optimization of the pair at the beginning. If you just have one picture, you can run an inverse render on top of that, and it's going to give you something which looks really beautiful and perfect from that one direction. But as soon as you tilt the camera a little bit, you will see that it's completely crazy what it made, and that it doesn't make any sense from other viewpoints as well. And so this kind of thing is always something you can avoid by having more information. That information can come in the form of additional views But imagine that your camera also has some kind of a depth sensor, right? That's something that can help out. When you capture polarization, that's something that I'm quite interested in. The polarization provides you information about what the materials are made of and in what direction they are oriented. So this also provides you information that goes beyond just what is available inside a single ordinary RGB image. So the more of this you have, the more it can also regularize the rendering process.
Yeah, I think it also goes, thank you, it also goes along with the next question, which is, what do you think about approximating parts of the physical process using deep learning, especially for complex scenes with many objects, with many BRDFs, bounces, and a number of samples that you have to?
Yeah, I think that sort of goes along the line of what I had mentioned earlier. People are sometimes looking at replacing part of the rendering algorithm with deep nets. And that's certainly something you can do, but then you have to teach physics to the deep net. So that means making a lot of training data, really spending a lot of time building a pipeline just to get it to recreate something very simple that's kind of trivial for a rendering algorithm. Of course, it might be a little bit faster at the end, but I'm wondering, now with all of the improvements that we have on, for instance, being able to do really fast hardware accelerated ray tracing, there might be a point where kind of the benefits that are to be had from this are not as significant as one would ordinarily think.
Yeah, and there's a last question in YouTube, which is, do you think it would be necessary to develop special hardware for differential rendering?
Yeah, that's a good question. Well, to be honest, I think now, with hardware accelerated ray tracing on chips and the ability to do really fast arithmetic, I think we're pretty happy with the hardware capabilities that we have currently. It's certainly much more efficient than doing things on a CPU. I guess hardware accelerated ray tracing is still something very new, and so the interface, how to get access to those kinds of functionalities can still be a little bit difficult. I think if there is a problem at the moment, it's more of a software problem. That oftentimes when we differentiate things, that means we have to generate a lot of code dynamically because nobody wants to calculate derivatives by hand. We have tools for transforming software into their derivative versions. And then when, as part of these operations, you're tracing rays, then very quickly you run into some pain points using pieces of software like optics from NVIDIA that then become a little bit difficult to use. And so I think those are things where maybe it's going to become easier in the future, but it's not really a hardware change that would be necessary there.
Okay, thanks. I'm done with the YouTube questions here.
Okay, so yeah, if there's no more question, let's thank again our speaker. Let's have a silent round of applause again.
It's a pleasure talking to you.
Yeah, thanks a lot, Wenzel, for the super cool talk. Thanks a lot.
All right, then have a good afternoon.
Yeah, you too.
Thank you.
Bye-bye.
Bye-bye.
Thank you, bye.
Thank you, bye.
Bye.